All right, everybody. Feel like it's working. Are there clicker questions? There are. Yes, we are going to do clicker questions today. I mean, with almost every lecture, we will have some sort of clicker question. So, thanks for asking, Jacob. I'll give people like a couple minutes, then we'll start lecture off. How's everyone doing? It's Wednesday. Halfway through the week. I do appreciate everyone who's been asking good questions on Campus Wire. I know and some of you guys came by office hours and asked about homework stuff, which is good. Great. Hi, yeah, I'm doing good too. Thanks, guys. Hopefully, yeah, I turned on like the ultra low latency setting on YouTube, so hopefully the latency between like talking and like comments is like super low. They say it's ultra low, so we'll see how low it is. It's probably like a second or two at least, but. Okay, cool. Let's start things off. All right, welcome everyone to week 1. I mean, today technically it's lecture 3, but in terms of the clickers, we're gonna call it like lecture 2 because our first lecture, which was really lecture 0, because I don't know, UCLA textbook store can't figure out how to like get my textbook out to people. But in any case, yeah. Good. Fedekai asks, how do we get the eagle on campus when we ask most of our questions during lecture? Well, you can ask homework questions on Campus Wire. Or you can ask conceptual questions, or you can ask, like, whatever. Yeah, and I always end up seeing this towards the end of the course. People suddenly start asking a lot of questions to, like, you know, engagement farming and whatnot. It's okay, as long as it's physics related, and again, not just like posting pictures of, I don't know, cute fuzzy animals and being like, hey, upvote this, please. But yeah, I mean, again, I don't want to discourage you asking questions during lecture. Like, please do that as well. That's the best way for you to get like help right away from me. But yeah, if you're working through the homework and things don't make sense, yeah, please feel free to ask the question on Campus Wire. Ooh, where are the discussion worksheets located? That should be in Brew and Learn, I believe. Yeah, you guys had discussion today. How did that go? Please let me know. And so they should be uploading that to Brew and Learn. I'll talk to Albert later today to see how his discussion went. It was fun. Okay, awesome, great. I'm glad it worked out. Yeah, he's a great TA, Albert. I love him. He's a good guy. He taught this class actually last quarter for Kosenko. So. What's your email to email me about a problem? Well, what type of problem? If it's a physics problem, as we said in the syllabus, which the syllabus quiz is due. The extra credit syllabus quiz, I think, is due at the end of this lecture today at 2 p.m. So if you haven't done it yet, please try to do it. Actual problem. So yeah, if you have an actual like physics problem, use the Campus Wire to submit it. If you have a problem with some sort of administrative thing, my email's inside Brew and Learn there. You can email me as well. Yeah. Cool. It was about the math. Okay, nice. Great. I'm glad it was about the math. Yeah. And you do get credit for answering, getting upvotes. So if you just participate, I think you should get credit for stuff. Also, I can kind of tell who's like being active and like doing things. So, yeah. Okay. That being said, yeah, we got quite a few things we got to go over today. So I'm gonna try to do my best. If the pace seems a little fast, it's all good. You can rewatch the recording later. I'll post it. And also, we have office hours. So I always tell students, if things were too quick and you couldn't get it during lecture, don't worry. Come to office hours. And in that environment, I have a lot more time that I can use to explain and make sure that things make sense to you. Okay. So the first thing we're going to go through today is Pascal's principle. Okay. Pascal's principle is really cool. And it's super useful in today's world in doing things like breaks and whatnot. So Pascal's principle states this. States that when you have a change in pressure applied to an enclosed fluid, as long as the fluid is incompressible, which most fluids are, the change in that pressure is transformed uniformly everywhere else. Okay? So the example they give here is that, for instance, if you had a... Oh, this is a little wonky. There we go. If you had, for instance, a cylinder of fluid and you had like a mass on top, right? You're going to have different pressures throughout the fluid, right, due to height. We know, for instance, here that the pressure is going to be higher because you have more liquid above it that is pushing down, right? And that's the rho GH that we learned yesterday. But let's say, for instance, I put a mass on top of this piston, right? And it starts to push the piston down. Okay. In doing so, that's going to add pressure. And that delta pressure, right, is going to be the same everywhere. So that does not mean the pressure is the same everywhere, but it means the change in the pressure is the same. So if this, for instance, goes up by, I don't know, like 40, let's say it goes up by like plus 40 pascals, then this also would go up by like plus 40. So that's the key thing. Yeah. Sibo says it. Okay. So where this comes in handy is when we're dealing with hydraulic systems. Okay. And I think the first question on your homework involved a hydraulic system, which was with brakes. Would the change in pressure propagate at the speed of sound in the liquid? That's a good question, actually. I believe it's instantaneous. But yeah, I don't know the answer to that. So let me see. I want to say it's instantaneous, but let's see. Okay, cool. Yeah. So yeah, you are right. Pressure changes in pressure do move as compression waves, which we'll learn later when we go over waves here. There are different types of waves. You have like transverse waves, you have longitudinal waves. Pressure waves are kind of longitudinal, I guess. And in doing so, yes, that does propagate at the speed of sound. Are we going to have to integrate pressure? I don't think so. Well, if it's in the homework, yes. But for the course of the lecture here, no, I'm not going to do any crazy integration stuff yet. But we'll see. Whatever's in the homework, if it starts like requiring integration and stuff, then yes. And we can go over examples of that during office hours if you want. I can teach it to you. But for now, like, I'm going to use the lectures just to I want to get through the concepts and make sure you guys understand the physics behind everything. And then later, we can go through the math. My general like consensus that I've gotten from students is they tend to not really like it when a professor just goes through like long derivations all day in like lecture. Like if they're just using the lecture to just derive shit all day, students tend to be like, okay, bro, but like, what does this mean? Like, what's the point? So derivations, I think, and you'll see this in like textbooks. The textbook manufacturers get snarky about this, or the authors do, I guess, sorry. They'll always say like, this is an exercise left to the reader. And basically they're saying like, go do this on your own. And the process of you doing that little side quest of deriving things will give you an appreciation for the science behind it. Yes. So, you know, you can tell me. I always welcome feedback in the class. The general thing I've gotten from students is like, can we just go through like problems and like understand how things work versus like just deriving stuff is boring and like puts you to sleep. Like, you know, I'm happy to derive stuff outside of class if you want, but yeah. But yes, okay, good question. So yes, the pressure differences do travel at the speed of sound in a liquid, which is quite fast. So it's, you know, I think in hydraulic fluids, they say the speed of sound is around 1,500 meters per second. So you're doing stuff on the order of milliseconds at this point. And for the physics here, we're not going to really worry about, you know, time delay of pressure. It's okay. But good question. Where this comes into play and where this is very useful has to do with hydraulic systems, pistons. Okay. So here's an example of a piston. Okay. So, correct. Sound does travel at different speeds depending on the medium. You are correct there. Yeah, that is correct. But for the purpose of this class, don't worry about, I'm not going to be tricky with that on you guys. Okay. So let's say, for instance, you have two pistons. This is called a hydraulic piston. These are used all the time in like brake lines, like jacks, forklifts, and it uses a very cool concept, Pascal's principle, in order to become like a force multiplier. And we'll show how that works. So let's say you have, some movable metal plate that is resting on top of two liquids. And let's say things are chill. They're at rest right now. Okay. And then you apply a force, F1, down on this small piston. Usually I don't know how many of you guys are automotive people, but this will usually be called the master cylinder. Just a little tidbit. If you ever see something like, oh, my master cylinder went out, it's usually the piston that you're using your foot or like whatever, your gear shift to change, to apply force. Now, when you apply this force here at this part of the piston, right, that's going to cause a change in the pressure, right, delta P, which we know is going to be equal, remember, pressure is equal to force over area, okay? So the change in pressure that occurs here is going to be equal to F1 over A1. And what we learned from Pascal's principle is that change in pressure has to be the same everywhere in the fluid. So also here, at this point, the contact point between the fluid and the second piston, this is usually called the slave cylinder. Again, I don't know how much longer these are names that have been applied to things for like decades, but I wonder if with how things are changing, if we will change the names of these things. We're like master slaves, a little like not culturally correct these days. But this has the same change in pressure, but this will be equal to F2 over A2. Okay. Notice that the area here on the master cylinder is smaller than the area here on the slave cylinder. But the change in the pressure has to be the same. So what that tells me is that F1 over A1 must be equal to F2 over A2. All right? And so if I want to rearrange this to see like what is F2, our new force, based on what my force was on the first piston, F1, I get that F2 is equal to A2 over A1 F1. So all I did is I just like put that over here and divided it, right? So this is a really cool thing, right? So this shows me that my new force is equal to my old force at piston 1 times the ratio of the areas. So if the area on piston 2 here is twice the area here, you're going to get twice the force. And this is exactly how, for instance, like floor jacks work. You know, if you've ever seen like what a floor jack is. Let's see, floor jack. Yeah, something like this, right? These things can lift like, yeah, look, 2 ton, 3 ton. This is an insane amount of weight that you can lift with, you know, just by just pumping something with your hand, right? And the reason for that is that one side moves a very small area piston, and then the other side is a very big area piston. And that creates like a force multiplier. So you doing, you know, applying like 10 or 20 newtons here can turn into like 300 newtons somewhere else, just by there being a difference in the piston areas. Fedekai says, say ignoring friction, when you add mass M on the small area piston, then will the large piston go up at the same rate that the small piston goes down? So that's actually false. The rate at which things go up and down will change. The force will be different, but this is a good question because some people say, oh, wow, you can get this force multiplier. Isn't that like violating some laws of like infinite energy and stuff, or like you're breaking laws of physics? Like, how can I just magically get more force? And the reason for that is that although, you know, the forces are not conserved, you're getting more force out. You are getting the same conservation of energy, okay? So let's remember from conservation of energy, right? That, you know, energy before has to equal energy afterwards, or for instance, like energy in equals energy out. Energy is also defined as like the work that's being done, right? And work is equal to force times distance. Correct, exactly, yes. So the amount of work that you do here, right, on this piston, will then have to equal the same amount of work that's being done on here on this piston. And if the force, right, is bigger here, that means that the distance must be smaller, right, in order for you to get the same amount of energy that's happening. So, yeah, you're not multiplying your energy. You're not putting in energy here and magically getting more energy out here. You're putting in a low amount of force over a greater distance, and you're getting a higher amount of force with less distance. So we still say that like energy 1 is equal to energy 2, right? The energy you put into here is the same energy you get out from here. Yes, exactly with the car jack. That's why you need to pump it multiple times. Yeah, you do this a lot. You're doing a lot of change in distance, right? And your car jack is moving up like a couple inches at a time. Exactly. Yeah, that's the trade-off. You're trading distance for force. And it's cool. I mean, I think it's pretty. I think it's dope.
That's dope.
Yeah, and it's the same thing with your brake system. I think there was a homework question over this. But when you apply like a force on your brake pedals, right? You're moving your foot probably like, you know, a couple inches, maybe even a foot, right? I don't know. It depends how loose your brakes are. Doing that, applying that force on the brake cylinders, the slave cylinders for the brakes, those brake cylinders only move like a couple centimeters, millimeters, honestly. But they apply so much force. There's such a force multiplier from you pushing your foot down that's what allows your car to stop. Yeah, so it's crazy, right? To think that, you know, me just applying a force with my foot can somehow apply enough force to stop like a 2-ton vehicle that's moving really quickly. It's because of hydraulics. It's because you get this force multiplier. But that's at the expense of distance. So you have to move your foot more in order for the brake calipers to move a little bit. The example of the needle, when the needle was smaller, the pressure was greater. Here the area is bigger and there's more force. How is that so? Okay, good. Because with the needle and stuff, it's not all the same fluid, right? So here with Pascal's principle, we're talking specifically about the change in pressure in like a fluid. With the needle, yeah, so with the needle, right? You're applying a constant force, right? And we're looking at what the pressure is at that contact point. This is not a fluid, right? Within a fluid, changing the pressure in one area, so for instance, changing the pressure here has to be the same as changing the pressure here. With the needle, when I'm like applying this to like my skin, the pressure is not going to be the same because this is not a fluid. So here the change in pressure is coming from there just being less area. Yeah, a little bit different, but okay. Yeah. Okay, it's cool. So that's Pascal's principle. Very, very useful principle. It gets used all the time. It's very cool. Okay, let's talk about buoyancy. Buoyancy is cool as well, right? Okay, so now we got to do buoyancy, which I believe is called Archimedes' principle. Let's see, where do they label this? Yes, Archimedes' principle. Right. Okay, here we go. So Archimedes' principle says that the buoyant force on an object equals the weight of the fluid it displaces. Okay, and then they use this equation. They say FB is equal to weight of the fluid it displaces. So how I like to let's see if they got a cool little picture for this. Yeah. Okay. Sure. I don't know if I like this picture, but we'll use it. With swimming, you know, you might notice it, right? When you're underwater, you feel like you're kind of getting like pushed up, or like things are lighter, right? You can lift really heavy weights underwater. That's because there is a buoyant force acting on something when it is submerged in a liquid. And so if, for instance, we were to look at someone swimming here, that person would have the weight of themselves, right? Which is the force of gravity, really. I don't like using the term weight, but let's just say the force of gravity here. And that's equal to the density of the person. For instance, let's call the density, here, let me use different colors and stuff. Let's use light green. Okay. So let's say the person has a density rho 1, and then let's say the liquid here has a density rho 0. Okay. The force of gravity acting on this person, right? We know that's equal to mg. And the mass of this person, right? Well, that will be equal to the density of the person times the volume of that person times g. Right? So mass, remember? Density is equal to mass over volume. So that means that mass is equal to density times volume. Okay? So this is what the force of gravity is that's acting on the person. That's gravity trying to pull them down. However, I think you've probably noticed, right, in the water, you don't immediately start falling down to the bottom. You also have some buoyant force that's pulling you up. It turns out that buoyant force, FB here, is equal in the opposite direction, so up, to the weight of the fluid being displaced by the object. So that buoyant force, which here we'll do here, force buoyant, would be the same as like taking a cutout of like the amount of liquid that the person displaces. Okay, so we can say, okay, that's equal to V times the density of that liquid, rho naught. Because here we could say this is M liquid times G, which is equal to rho 0 V times G. And that's how you get the buoyant force, which is pushing up. So if you wanted to then figure out the net force acting on the object, right, that would be equal to this minus this. Yeah, this is kind of cool. They show here actually like the free body diagram for the liquid, which, yeah, the liquid, right, should just be chilling. It should be just staying still. So the liquid feels Fg of the liquid pulling it down, and then it has the buoyant force of the liquid pulling itself up. That's why liquid doesn't like keep falling down. It actually does in nature with what's called like temperature gradients, and it's actually a really important thing for what is it, for like the ecosystem. Let me get it real quick. There's a name for this process. ecosystem liquid falling down. I don't know. We're gonna like. It's like a. Yes, here we go. This is really cool. Just a little bit of yeah. So for instance, during the summer, I don't know if you ever noticed if you jumped in a lake, right? As you go further down, right, the water gets like colder, and colder water is denser, technically. And so what happens is then as things get cold, right, up top here, what ends up happening is the water on the top that's getting more dense as it cools down starts moving down, and as it moves down, it starts pushing the water on the bottom back up, and you get like this turnover thing. And so this is important because this like cycles the water naturally within a lake. And then during the winter, this is again the really nice thing about ice, like solid water being less dense than liquid water, is that the ice on the top actually insulates the water below, such that it can never be below 0 degrees in the water. It's actually, it's a little bit higher, 2 degrees, 4 degrees, and this is what allows life to still live during winter. Otherwise, like everything would die. Everything would die in the winter, and we probably wouldn't be here. So, but sorry, back to Archimedes' principle. So, in this case, we're going to assume the water is all the same temperature in whatever body of water you're in. So the water stays still, and thus the buoyant force and the weight of the fluid is the same. And so when calculating the net force on something that is in a liquid, you have to calculate the force of gravity that's pulling it down, and that's the density of the object times the volume of the object times g. And then you have to calculate the buoyant force, which is the density of the liquid times the volume of liquid that's being displaced, which is usually it has to be, right, the same as the volume of your object that's in the water, and then times g. So these two fight each other. And depending on this versus this, right, this is why things sink and things float. Because if the density of an object, right, is higher than the density of the liquid, then the force of gravity beats out the buoyant force. And this is why things sink, right? Here, we'll just draw like a little free body diagram here, right? So you have, this is force buoyant, which is equal to rho naught Vg. Let's just say this is like rho naught. And then this is rho 1, which is the force of the liquid, or force of gravity, sorry. And that's equal to rho 1 V times G. So yes, if the density of your object is greater than the density of the liquid that it's inside, this beats out this, and that's why things sink. If this has less density, right, if your object is not as dense as water, such as if it's oil or like wood or something, then the buoyant force beats out the force of gravity, and this is why things float. So it all comes down to this. Cool. Makes sense? All right. Let's see what else we have. Characteristics of flow. I'm not going to really go over this. Ooh. Flow rate and velocity. Yeah, this is important. Okay. Because this is going to get into flux, which we are going to like kind of do when we get into electrostatics. Right, here we go. Okay. So, within, let's say, a tube of liquid, and the liquid is flowing, right? You can have something which is called the flow rate, okay? Which is volume flow rate, which is the change in volume of liquid over the change in time. This is a derivative, right? dV dt. Now, if we're to break that down, right? Remember that volume is equal to like some cross-sectional area, which in this case is this, times x, which is, for instance, the volume of a cylinder, right? That's the cross-sectional area here, pi r squared, times the length of the cylinder, which is x, okay? So if I wanted to get dV dt, assume that the cross-sectional area is not changing, right? Let's assume it's just a straight pipe. then what you get is, because A is a constant, right? If you take dv dt, which is d dt of ax, the A just comes out because the area is not changing. And then you get A dx dt, or you get A times v, right? So dx dt can also be thought as the velocity of this column of fluid as it moves in a pipe or something, right? And so that gets us what's called flow rate, Q, which is going to be equal to AV. And then the important point about things is that the flow rate in different parts of a pipe needs to be the same. It's like, and that has to do with if a fluid is incompressible. So here we go. So here's because you may be asking, this is where this comes up. It comes up with this. If you have, like, for instance, you've probably seen this. You know, if you guys have ever had like a water hose or something, and you notice that like water's coming out, right? And then if you like put your finger over it, or like put a nozzle on it to try to, like, you know, decrease the area of that hole, that the water seems to shoot out faster. Yeah. That has to do with this, which says, what are some conditions to reach laminar flow? Oh, that's good. Yeah, that's like, I think incompressible fluid is important. And then, yeah, you need like smooth walls. Like, you can't have much friction between the pipe walls and the fluid. Oh, wait, no, sorry. You want a lot of fluid. Yeah. Yeah, here we go. That's a good question. Laminar flow versus turbulent flow. How do we consider viscosity? Yeah, so viscosity is going to be resistance to flow. I don't think we go over viscosity in this class. I don't see it. I don't see it as one of the topics. But in general, things that are more viscous it's kind of like, it's like liquid resistance is what it is. Higher viscosity things tend to kind of like resist flowing as much. But anyways, the important thing here is that due to like the continuity of fluid flow, and due to the fact that most fluids are incompressible, the same amount of fluid must flow past any point in the tube at a given point in time. You have to have the same Q everywhere. So we say that Q1 here, which is equal to A1 V1, must be equal to Q2 here, which is equal to A2 V2. Okay. So if you start decreasing the surface area of your pipe, you go from a big pipe to like a thin pipe, that means the velocity must go up. And so you probably see this with like hoses and stuff when you do things. So that's another important quantity. It also has to do with like conservation of mass. Yeah, mass flow rate. Yeah, okay, cool. Anyways, okay, good. All right, so the next thing we need to do is, does shear play a role here, or do we assume, so all parts of the fluid, they actually move slower closer to the edge than they do in the center. So yeah, that's a good question. Whenever we're doing V here, we're considering the average flow, which is the flow in the center. Okay. Yes, exactly. Yes, good, Sophia. Yeah. Yeah, what happens is here we go. This is like laminar flow versus turbulent flow. We do assume this, right? Okay. Such that liquid, and this has to do with like what's called like a boundary condition, right? The fluid flow here has to be 0 at the edge, right? Because eventually you hit the edge. And if not, you would have like a discontinuity in fluid flow. So you get a velocity that looks like this. The fluid moves the quickest in the center and then starts to decrease as it goes towards the edge. And this is continuous. But for the purposes of this class, we will usually consider the average velocity to be it. When we consider high viscosity fluids, we need to take into account shearing forces. Yes, this also has to do with like Reynolds number. Again, more advanced topics that are very cool for like there are entire classes dedicated to fluid dynamics. There are entire labs, entire research things. But for the purpose of this class, because we only have like 2 days to go over fluids, we're not going to go super in depth into like Reynolds stress and all the viscosity stuff. Will we need to derive the velocity profile? I don't think so. No, I'm not going to do that to you. I think, if anything, we're just going to have you derive like, hey, what's the velocity of the fluid here compared to the velocity of the fluid here? And it's, again, using simple conservation of, conservation of Q, conservation of flow rate. Yeah. Okay. The other thing we need to do is Bernoulli's equation. Okay, Bernoulli's equation is very cool. And it's named after David Bernoulli, but it refers to a variety of changing things that can happen within a system of flowing. Okay. So, where's the full equation for this? Here we go. This is Bernoulli's equation. Good. It states that the total, like, ambient pressure plus what we call, this is like the pressure due to velocity flow plus the pressure due to changes in gravity in one condition have to equal the same things in another condition, right? So if fluid starts moving up in height, right, that means you have to start decreasing stuff in other places. This is very similar to what we did in mechanics, right, with conservation of energy. We learned about gravitational potential energy, kinetic potential energy, spring energy, friction energy, and all the totals of the energies in one condition had to equal the totals of the energies in another condition. It's kind of the same thing here, but we're talking about pressures due to like fluid flow. And those pressures can come from, again, some ambient pressure, P1. Sometimes this is like P atmosphere, right? You can have pressure due to things having velocity. This almost looks like kinetic energy, right? See how this looks like 1/2 mv squared, and then this looks like mgh almost. So it's pretty cool. This is why I say that, doing physics, you start seeing patterns, and things start having like similar forms. I think you also remember seeing it in mechanics, right? When we did like linear motion, the kinematics equations, and then like the rotational ones are like similar. You just add like a times R on it, right? V becomes R omega, A becomes R alpha. It's the same thing here with conservation of energy and fluid flow. To me, I start thinking like, oh man, maybe we do live in like a matrix, or like there is like some like programming to the universe because everything seems to follow certain rules. Yeah. How do you force laminar flow? Oh, okay. I think in order to force laminar flow, you just need to make sure that your liquid is incompressible. And then also there has to be, it's called Reynolds number, which measures how much the viscous forces change in comparison to like the inertial forces. So you want like low viscosity fluids in order for you to have like laminar flow. Yeah. And then, yeah, you want things to be like smooth and stuff. Reynolds number is the big thing for laminar flow, but again, we're not going to go over Reynolds number. There are entire classes dedicated to fluids that can go over Reynolds number. Anyways, so this is the important thing to learn here, is that the amount of this is equal to the amount of this. Good. What is the rho g y1 term? So this is like gravitational pressure. Right? So remember Anurag, right? When we had some sort of like liquid, right? And there was like a height of fluid here. Depending where you were, right, you would then have rho gh, this amount of fluid exerting pressure on you here. So that's where this is the gravitational pressure. But then there can also be pressure due to things having velocity, like moving at a certain speed. In this case, like things weren't moving, so we don't really worry about it. And then you also have like what's called like the ambient pressure. And so this can be for instance from like P atmosphere, can be like P1, or it could be again like a piston exerting a force on it, right? Okay. So that being said, let's do some clicker questions because yeah, we got a little bit of time here. Let's see. Okay. If we go to here, if you multiply volume to each side, the dimension will be J. Then what would rho V? Oh, I see. I see. Rho V would represent the mass. Yeah. Right? Because it's density times volume. That would just be the mass. Yeah. Okay. So if you go here to Kudu here, you should see that we have a second set of clicker questions up. And so here's the first one. Let me paste this in. And then, here, let me get the answers for this one. This was question 1. Okay. So can write the correct letters. What is the sensation? What'd you send me, dude? Let me pull this up. Oh, these are. Oh, okay, very cool. Yeah, these are. Yeah, good. Thanks, sensation. Yeah, these are. Oh, this is how you can do it with. Yeah, this is writing the Greek letters, I guess, in HTML and stuff. Oh, that's cool. Yeah, we're gonna use a lot of Greek letters in physics. You already know this, right, from mechanics. There's a lot of Greek letters that we use with things. Okay, but here, let's try to do this question here. So it says a tank is filled with water to a height of 7.1 meters. There's a small opening in the wall at a height of 1.27 meters. The water is running through the hole, hits the ground at a distance L from the tanks. Calculate L. Okay, so if you already know how to do this one, you can try to do it yourself again and answer it. See if you get your one attempt right. Otherwise, we're gonna go through it here. But okay, so there is a simplification to figuring out the velocity of the water that is coming out of a like a cylinder of water, and it has to do with, I think they call it like Torricelli's law. It's actually pretty cool. It comes from Bernoulli's. Okay, so Torricelli's law. This one says that the velocity of liquid coming out of an object is equal to the square root of 2g, and then we say like delta y. So it's like the change in the height from where the top of the liquid is and then where the liquid is flowing out from. And that comes from this equation right here. So let's pull it out. So again, this comes from like Bernoulli's equation. So if we consider, right, two situations. Let's consider, here, let's say this is like situation 1, which refers to the water right here. And then let's refer to this as like situation 2, which is the water at the hole where it is falling out. All right. We can write out our Bernoulli equation for what's happening at situation 1. Okay. So you have P1, right? That's the ambient pressure. And that right there is just going to be equal to P atmospheric, right? We're going to say this is like P atmospheric. Let's call this, for instance, this is what they call like the common datum. You have to just note that there's some location where h is equal to 0. Okay. So we're going to call this y is equal to 0, right? Okay, so the next term here is rho v1 squared. So this is referring to the velocity of the water at situation 1. We are going to assume that the velocity of here is pretty low. It's basically 0. Okay? Because if this tank is big enough, right, and this hole is small enough, then the rate at which this liquid is moving down will be very slow compared to the rate at which the liquid here is flowing out. And that also comes right from Q1 equals Q2. So A1 V1 equals A2 V2. So if this is very big, then this will be small. If this is very small, and then this is very big. Right? The other way to rewrite that would be that like V1 equals A2 over A, or no, sorry, V1 is equal to A2 over A1 V2, right? So if wait, what else? Right, A2 over A1 V2. So if this area here is much bigger compared to this, then this term basically goes to 0. Right? We do this in physics a lot. We take like limiting cases. We say, oh, I can start dropping terms because if A1 is much bigger than A2, then A2 over A1 is basically 0. And so that tells me that V1 is basically 0. So this will go away. We're going to call this 0. And then rho g y1, okay, that's going to be rho g, and then y1 is the height of this liquid, referenced to my 0 point, all right? And here, if I called this 0, right, then this height, y1, is going to be equal to big H minus small h, right? You see how we get that? So this is going to be h minus little h, big H minus little h. Okay, cool. And so now we've gotten all the stuff for situation 1. Now let's look at situation 2. And here, let me move this stuff down a little bit. Kind of like a justification for this. So here, you're also going to have atmospheric pressure, right? Everything's still open to the air, right? So you have atmospheric pressure. Now we're going to have 1/2 rho V2 squared, and this is not going to be 0, right? Because this is flowing pretty quickly. And then we're going to have rho g y2, and since we called this height 0, that means this is 0. So now, setting them equal to each other, I'm going to have P atmospheric plus rho g big H minus little h is equal to P atmospheric plus 1/2 rho V2 squared, okay? You should start noticing some things, right? P atmospheric here is going to cancel. We can also divide by rho. Do you see how, like, now I have just rho being multiplied on both sides, so I can divide by rho on both sides. So that's going to go away as well. And what we're left with is G, H minus little h, is equal to 1/2 V2 squared, which, now rearranging for V2, you get that V2 is equal to the square root of 2G big H minus little h, which is the same thing here, right? This is Torricelli's law. So the velocity of liquid from a small hole in a big container, big tank, is equal to the square root of 2G times the difference in height from where the top of the water is to where the hole is. So this is a useful equation. But it comes from Bernoulli's equation, right? So what we can do is we can now use our equation here to figure out what the velocity of the water is from out here, right? And so, what color did I use for that? I used pink. I like pink. Yeah, pink's fine. Okay. So here we can say the velocity here is going to be... Couldn't you use the bottom as 0? Correct. Yes, you could as well. So the same thing as with... Remember, like, conservation of energy with gravity stuff in mechanics? You can call the height whatever, you can call 0 wherever. It will come out anyways. So if we called this 0, for instance, Amadai, then yes, this height would now have become big H. This would have become little h. But when you move it over, you still get big H minus little h. So you're right. The math would still work out. So this is equal to the square root of 2 times 9.8 times my big height minus my little height. So that's going to be 7.1 minus 1.27. Okay. And doing the math there, here, I'll pull my calculator out so you guys can see what we're doing. Square root of 2 times 9.8 times 7.1 minus 1.27. That's going to give us a velocity of 10.69 meters per second. Okay. So that right there, right? That's our new velocity. Now they were asking, calculate the distance that the water travels, like this distance L, for it to hit the ground. So now this is a kinematics thing. I mean, this is what I think this is always so cool with physics, is that everything you learn kind of builds upon itself. So now we're going back to what you learned in 1A, which is figuring out from kinematics, if water has a velocity, a horizontal velocity here out to the right, how far is it going to travel before it hits the ground here, if this is the height h? So from kinematics, right, we know that this distance L is going to be equal to Vx times t, which is going to be equal to my 10.69 times the time the water's in the air. And to figure out the time that the water's in the air, we can use our kinematics equation in the y direction to then determine how much time it takes for the water to drop. So that comes from this, right? So we can say like h is equal to, and since the water is being thrown out horizontally, it has no initial velocity in the y direction. So we can say 0 is equal to h. It doesn't have any, no initial velocity in the y direction. So this is plus 0t, and then it's minus 1/2 at squared, which is going to be minus 4.9 t squared. So then that tells me that t is just equal to, what's that going to be? It's going to be h over 4.9 square rooted. So, doing that, we get that the time is equal to 0.509 seconds, okay? And now I can take this time here, plug into here, and this will give us the correct answer of 5.44 meters, okay? So in this case, the correct answer, so 5.4 meters is answer choice C. And so that's what you want to do. So again, here within Kudu, if you go here and you choose C, and we say check answer, look at that, it's correct. I'm so glad when technology works. Anyways, okay, does that make sense to people? This is a cool problem because, again, it deals with Bernoulli's equation to figure out the velocity of the water falling out, and then it deals with kinematics to figure out how far it travels. Okay, so then here's a follow-up question to it, right? Where we say, okay, a stream of water escapes through a small hole from a barrel filled with water. If you double the area of the hole, the velocity of the stream will, question mark. And then here are the answer choices. So do we think that the velocity of the stream will double? Do we think it'll increase by a factor of 4? Well, that should say of 4. It almost says if 4, of 4. Or do we think it'll decrease by a factor of 2? Or do we think it'll stay the same? Okay. Sid thinks it's decreasing. Okay. So you would be right if, for instance, we're talking about a pipe, right? If we're talking about like a solid pipe here, where we're going from fluid flow here to here. Yes, A1 V1 must equal to A2 V2. So if this goes up, you would think that the velocity of the stream would decrease, right? That's for continuous fluid flow within a single pipe. However, this is considering fluid going from a container out into just the air, right? And if we notice, right, when we did our equation here, did we ever talk about how big the area of the hole was? Not really. I mean, we considered it here, right? We considered that the area of the top of the cylinder must be really big compared to the area of the hole. So it would not change. Yeah, because remember, let's look at our equation here. When we derived it, we got to here. There's nothing here that deals with the area, right? We didn't even take into account. We used the assumption that the hole is smaller than the area of the tank. So in this case, I think doubling a small number is still kind of a small number. If, for instance, I don't know, if we increase the area of the hole by like a factor of 1,000, then yeah, things would not stay the same, because then this approximation doesn't hold anymore. But the key thing here is that, like, doubling the area of the hole is still small, so we still assume that the velocity of the water at the top of the tank is 0. Without the assumption, does it decrease? Yes. So in the case of, by this here, right? If this were to get bigger, right? Now your velocity at the top, right, is not 0. And if this is not 0, right, now you have more terms here, which means that this must go down. You're right, 1Z. Yeah, so essentially the great pressure difference here in comparison to the minimal changes in pressure within the pipe with continuous flow is the reason. Yes. The main assumption here we make is that the velocity at the top of the cylinder is very small compared to the velocity that is coming out. At some point, yes. If for instance, this tube was like, the hole was like the size of the whole container, then you kind of have this situation, right? Because now whatever water is coming out here is the same amount of water that's coming out here. Yeah. Yes, it is under the assumption of the velocity, right? It's under the assumption that the velocity at the top is 0 or negligible, because the area of the hole is still much smaller than the area of the top of the cylinder. So mass flow rate is still comparable. So you still do have conservation of mass flow rate. That is correct, right? Which is like MV equals MV, right? But M, let's remember, is, so MV here is like rho A dy dt, right? And if the area is very big, then dy dt is small. So if you have a big cross-sectional area here, then the amount that it drops, dy dt, is going to be small, compared to if you have a big thing here, then dy dt is suddenly not small. What is the maximum size of the hole before the velocity of the fluid decreases? I mean, that kind of comes down to, like, at what point do we no longer consider it to be the approximation for it to be 0? I don't think there's no set number for that. Yeah, exactly, because the float is about 0. I mean, no, you are right. Yeah, so I can't say that there's a specific number that it would be. This is in physics where we just say assume. I know they call this hand waving in physics. I don't like it, but this is how they structure the question sometimes. Because you are correct. Like, technically, it does decrease, but the point of this question is that it decreases so negligibly that you don't need to worry about it. And as crazy as this sounds, this is a common thing we do in physics, where, and this is why math people get, like, super upset. because they're like, whoa, bro, you can't just make approximations. But in physics, we have to make approximations. Otherwise, carrying like terms like through like very elaborate and very like drawn out situations becomes an absolute mess, and you can't solve things anymore. So the classic analogy here is that like you have like a math person and like a physics person, and you have like an engineering person. I guess that's the third one they say. But it's like all the people are standing like 10 meters away from a cup of ice cream. And you say that, okay, every 5 seconds, the distance between you and the cup of ice cream goes down by a factor of 2. Like it halves. The math person would say, like, you never get there. Like, you'll never touch the ice cream because you're always like decreasing, right, by a factor of a half, but you'll never actually get to where it is. Whereas the physics person says, well, okay, after about 100 seconds or whatever, the order, the difference, the distance I am away from the ice cream is basically 0. Good, like sine of x is equal to x. Correct. Yes. We do that in, you probably haven't taken optics yet. I think that's physics 1C. But yes, the small angle approximation for sine of x is basically x. 100%. That's the same thing. Because if you're to carry things out with sine, instead of just saying it's x, the math gets like infinitely like more difficult. So I know this is, while again, math people might throw up their hands and be like, bro, no way. Like this like breaks my laws of reality. You want to learn this early in physics, which is to just drop things based on like reasonable assumptions. What does the engineer say? Yeah, I gotta remember what the engineer says. I think the engineer just like builds a rocket ship and just gets the ice cream. I'll find the joke for you guys. It's a funny one. It actually involves like it's a bunch of guys at a bar and they're like trying to talk to a girl and they talk. I don't know, but it's whatever. I'll find it. It's a funny one. Okay, so the correct answer for this one should be that it stays the same. And that was answer choice D. Question 2. Why is D not the right one? Man, I swore I checked all these before we started. One sec. One sec. Hold, please. Clicker. Oh, it worked for you? Oh, why the fuck did it not work for me? The hell? Okay. You know what? Let me check. Maybe my thing's just like goofy. Let me see. Come out. Well, I'm glad D worked for you guys. I don't know why it didn't work for me. Oh, it is correct. Oh, sorry. It did work for me. Sorry, I'm bugging. Sorry, I have like PTSD from this not working yesterday. I hate when technology doesn't work. Especially like, yeah, okay, it did work. You know what like bugged me out here, guys? It's because I saw this red thing here saying last attempt, and like red means bad. I'm like, oh, I must have screwed up. But sorry, I'm getting used to it too. The green check mark means we're good. Yay, nice. Okay, cool. All right, answer choice was D. Almost had like a little bit of a heart attack there. Because I took time before this class. I went through and double checked the professor's stuff. I'm like, I want to make sure this is all correct. I don't want any mistakes happening. Okay. All right, let's go to the next question, which involves 2 identical barrels, each with a small identical hole at the bottom. One barrel is filled with mercury, one with water. What can you say about the fluid velocity of the mercury and the water coming out of the hole? Thank you. Yeah, thanks, guys. I appreciate checking my sanity. Okay. It always says last attempt. That kind of bugs me out, saying last. It shouldn't say last attempt once you get it right. It should be like, hey, man, you're good. Like, you don't have to attempt. Actually, it grades it out, right? You can't do any more attempts. I'll talk to the devs. I'll tell them, yo, fix that. Okay, here we go. So, same question. We're asking about, like, what happens if we change the density of the fluid. And, again, if you look at, like, how we derived this, right? This velocity had nothing to do with the density. The density canceled out here, right? When we saw rho g h minus h equals 1/2 rho v squared, we were able to cancel out density on both sides. So in this case, they should stay the same. Yeah, so they should come out with the same velocity. I agree. So let's see. Answer choice B correct. Yes. Good. Okay, cool. All right. The last question we got to do is a little bit of buoyancy. This is actually a fun one. See if I can get this one right. This one's going to be interesting. Good. Onesie says how though. All right. Well, let's go through it. So this is the same situation that we've been going through, right? You have a barrel filled with a liquid, and you have a hole at the bottom or like midway up or whatever, and you want to talk about the velocity of it coming out. Intuitively, we are moving something with more weight the same distance, right? Yes. So we're not worrying about viscosity though. We're ignoring viscous forces. We're assuming that you have laminar flow. Viscosity would start playing an effect here. Yeah. Again, we make assumptions where we say ideal worlds. Did your professors ever do like, the spherical cow? Right? Where there's like, oh, assume a spherical cow. It's like cows are not spherical. But for the simplicity of doing the problem, we assume that it's chill. It's a sphere, It's kind of the same thing here. We're assuming viscous forces are not messing things up. We're assuming laminar flow, low Reynolds number. You mean like a burger? Did they serve spherical burgers? Yeah, so Moses, you are right that the fluids are slower. But remember that also if fluids are denser, they have a bigger force of gravity pulling them down, right? Because remember that F is equal to mg, right? So the more mass you have, the more force you have pulling down. And so that's why increasing the density increases the gravitational term. By the same amount, it increases the kinetic flow term. And so the density cancels out. So yes, you have more inertia, so it should be harder to move, but also you have more force of gravity because you're heavier. And that's why it goes down. Thanks, Famished. Yeah. Does that make sense, Moses? Yeah, you are moving something more weight the same distance, but you have more gravity. You have more force of gravity pushing it. Yeah, really cool. Yeah, nice. Good. Glad. Okay. Let's try to do this question. I'm going to try to do it in the next 8 minutes. Okay. All right. It says a cube of unknown density rho naught is placed in two different density fluids. I'll go over that onesie in a second. Let me make sure I can get this one done in the amount of time. Rho 1, rho 2, the height of the cube is a certain amount above. This is like, they say the boundary of it. Calculate the density of the cube, rho 0. Okay? I'm going to do things all in terms of symbols, and then we'll plug in numbers at the end. Okay? So if we were to look at a force diagram on this, right? I'm going to break it up into two regions. I'm going to say I have a rectangular prism here, right? And then I have a rectangular prism here. And we're going to look at what the net force from those things are on each thing, right? Okay. So, looking at the top part, right? That's going to have a force of gravity pulling down. And that is going to be equal to the mass of this top part, which is rho naught, right, times the volume of it, times g. That pulls down. That's a minus, okay? That's the force pulling down. But then we have a buoyant force, right, from the amount of liquid that was displaced by the top part of this cube. And so that's going to be plus rho 1 v times g, okay, of the top here. Now, this volume, right, if this is a cube, that means that the top, right, has, the same, width and same depth this way. The volume is going to be equal to that surface area times the height. And because it's a cube, right, the surface area is going to be the same everywhere. So here we can say, all right, cool. This is negative rho naught. I'll put A in there just for whatever. And then we're going to say this is H1G. And then this is plus rho 1 A H1G. Okay? That is the sum of forces on the top part. Okay? Now let's look at the sum of forces on the bottom part here. Okay? So now I have this mass of the cube pulling down. So that's going to be negative rho naught A H2G. Right? Because that's mass times volume of this. And then we need the buoyant force from liquid 2, which is going to pull up. And that's going to be plus rho 2 A H2G. All right? And then what we need is we need the sum of all of these forces to be equal to 0. So when I add up all the forces here, right? The force of this pulling down, the force of the liquid pulling it up for the top part, the force of the gravity pulling the green part down, and the buoyant force of liquid 2 pulling it up. Once I add up all these forces, the net force should be equal to 0. So what I can then say, right? So I have in here, let's move this over. This was the sum of the forces on the bottom. And then we're going to go sum of forces equals to 0. You're going to have, can I highlight it? Come on, girl. There we go. Nice. We're just going to add them all up, and then we need this to equal to 0. So some things we'll notice, right, is that the area, cross-sectional area, since it's the same, it's a cube, right? Cross-sectional area of a cube is the same throughout all parts of the cube. That's going to cancel out. I also notice G is going to cancel out everywhere. Goodbye. Right? And so what we're left with is negative rho naught H1 plus rho 1 H1 minus rho naught H2 plus rho 2 H2 must all be equal to 0. And then what did they want? We have H1, we have H2. Oh, they just wanted us to calculate. This is always good in physics. Like, figure out, what the hell are we solving for? Oh, we're solving for rho 0. So this is our, this is the thing we're looking for. And everything else we have. We have H1, we have H2, and we have the densities of the different liquids. Okay, so now you can rearrange things. So I'm going to say, sorry, rho 0, and I'm going to pull a minus sign out. Yeah, let me pull a minus sign. And this is going to be H1 plus H2 is equal to negative, and then that's rho 1 H1 plus rho 2 H2. Cool, minus signs are going to cancel out. I'm just doing some fast math here. So rho 1 H1 plus rho 2 H2 all over H1 plus H2. Okay, and let's make sure I got the right numbers for this. Rho 1 is 800. Okay. So we have 800 times H1 is 5.5 centimeters. Make sure you use the right units. So 0.055 plus rho 2 is 1,000 times 0.0848. Okay, it's all that. And then we divide it by the heights combined. So the heights added to each other. So that's 0.055 plus 0.0848. And so I do this right. Let's say 8.48, 0.055 I get 375. Let me see what they got. I put 100 in. Thank you. Thank you, Sib. I'm like, why am I getting the wrong answer? Yes. Clerical errors. You know the joke is when I was in middle school, they did one of those like, what is it called? Like career test things where they say like, take this test and see like what career you should have. And mine said I should be like an accountant or like clerical work, which obviously not. Good. There we go. Thank you, Sib. Yes, I appreciate that. Good. So now we get that rho naught is equal to 921, and that's going to be kilograms per meter cubed, because that's what all the other densities were given in, right? Okay, oh, and I need to show you guys what the answer choices are. Usually I'll put these up ahead of time so you guys can see them and solve them on your own, but we were kind of running out of time, so I just wanted to do it. Where is it? There we go. Those are the answer choices. So the correct answer choice, choice B. Okay, so if we go to Kudu, put answer choice B. Is it correct? It is, yes. Okay, cool. All right, thank you everyone for coming. That wraps up lecture today. I hope you guys, we did a lot of stuff today because I had to wrap up fluids today. So, again, if anything didn't make sense or was confusing or we went too fast, you can rewatch the lectures. I'll post the recording for it. I also have office hours later today at 5 o'clock. So please feel free to come on by. It's the same channel. The numerical answer was 921. Yeah, answer choice B is what we got here. But yes, thank you guys. Our next lecture will be tomorrow, same time, same place. Make sure you do the extra credit stuff for the syllabus. I think that's due today. Also, we will release a new chapter tomorrow, either later tonight or tomorrow morning, and then the pre-lectures for that will be due on Friday. So I'll let you guys know. All right, cool. All right, enjoy the rest of your Wednesday. We will